Lesson 2 in chapter 14 on sound. We're going to begin by looking at spherical, three-dimensional surface, and plane waves. Now, when we talk about this word plane, we're not talking about an airplane or anything like that. We don't mean by the word plane everyday or ordinary. That would be spelled differently. We don't think about the rain in Spain stays mainly on the plain, if you know that old musical reference. By plane here, we mean a flat two-dimensional surface. For example, a plane in the XY coordinates or in the XZ coordinates and so forth. And we're going to begin by talking about what we call a point source. Imagine, and now we're looking at this diagram down here, figure 14.5 on the left, and imagine at the very center in the middle of that blue circle, we have a speaker that can produce sound in all three dimensions. And so you're looking at a slice or a two-dimensional cross-section of a three-dimensional region of space, and the sound is going to travel in 1 unit of time. Let's pretend that unit of time is a second, and then 2 seconds later it's going to be a little bit farther, and 3 seconds later it's a little bit farther, and 4 seconds it's a little bit farther. And let's also imagine that the area around in here where it's kind of dark is up to the actual black line is going to be a compression. And let's say that this area here that's lighter in color, kind of faded, let's say that that's the rarefaction. So you have compression, rarefaction for every single wave as the wave emanates outward from the point source in 3 dimensions. Now, just like if you have a balloon where the polymer, the material out of which the balloon is made, is pretty thick when the balloon has only a little bit of air in it, but as you blow that balloon up and it gets bigger and bigger, in other words, as the radius gets greater and greater, the thickness of that material out of which the balloon gets thinner and thinner. In the same way, the intensity of the sound, which is measured in terms of the power, the wattage per cross-sectional area, the intensity of the sound is spread out over a greater and greater surface area as the sound moves farther and farther away from the point source. In other words, we say that we have an inverse square law here. The intensity varies according to the inverse square of the radius. So inverse means 1 over, it's in the reciprocal, and r squared comes because we're talking about a two-dimensional surface, which is the surface of the balloon, or in this case, we're not talking really about a balloon, but we're talking about the surface of this imaginary sphere representing the energy per second of the sound wave being produced by the point source as it moves farther and farther away from the point source itself. So this equation right here says that the intensity of the sound is that power, the energy of the sound being produced per second, per period of time, divided by the area over which that compression is distributed in 3-dimensional space around the point source. Now, if we look at these two equations down here at the very bottom of the page, if I multiply both of these equations by the radius, I get r1 squared there, and over here I'm going to get r2 squared, and that's going to be gone. And so now you can see that the average power over 4 pi, the average power over 4 pi are the same thing. And so we could say if A equals B and B equals C, that therefore A equals C. In other words, r1 squared I equals r2 squared I2. And you've done this with gas laws before when we begin to create an equation. And so when we move to the top of the next page and we rearrange our terms, we get this equation right here, an expression of the inverse square law focusing on just the radius and the intensity of that sound wave. Now, in the next three pictures, you're going to see a pattern develop that as you move farther and farther away from the point source, these rays that emanate from the center, which are always perpendicular to the surface of the curved wave, when you move from figure 14.6 to the bottom left, figure 14.7, to the bottom right, figure 14.8, the farther and farther away you get from the point source, the more and more parallel the rays become. So back up here in the upper right, you've got a certain angle theta, let's call it. And then way back here, notice that theta gets even smaller, and eventually theta approaches 0. And then in the bottom right, for all intents and purposes, when you're a significant distance away from the point source, these rays are coming out just about parallel to each other. And that's when we call this a plane wave or a plane wave front. Now keep in mind again that for the sake of comparison, we're letting these slices of the space through which the sound wave is traveling, pictured here in beige, representing the compressions where the molecules of the medium are squeezed together, and the spaces in between them are the rarefactions where the molecules are quite spread out. And this would represent the sound wave as it travels through space, three-dimensional space, from the point source of the sound wave. So that would be the difference between a spherical wave near the point source versus a plane wave significantly, we could say, a great distance away from the point source. And here, of course, now we can measure the wavelength from one compression to the next compression, with the wavelength being the distance. So let's look at a math problem here. We have a small source emitting sound waves. The power is 80 watts. So we're talking about the power of the sound. You know that light also is measured in watts, the amount of energy that the light has, the photons of light have per period of time. So you could have an 80-watt light bulb. Now, I've never seen one of those. You see 100-watt light bulbs and 60 watts and 40 watts and so forth. But so this would be less than a 100-watt light bulb in terms of the amount of energy per second. Remember, power is work per unit time, and work is measured in joules. So part A says find the intensity 3 meters from the source. Part B says at what distance would the intensity be 1/4 as much? And then part C, find the distance when your intensity is cut in half and goes from 80, the sound intensity is 40 decibels, excuse me. So part A, we're simply going to take our equation that connects intensity with power distributed over the surface area, and we're just plugging our numbers in. Not a very difficult math problem. Part B, at what distance would the intensity be 1/4 as much? So we're going to take this equation in the box, solve it for R. So there's your square root on both sides in order when we solve it for R. And once again, we're going to plug our numbers in. We know the power output is 80 watts. That's given in the problem. And we just already solved for the intensity I in the previous part A of the problem. Here's where the 1/4 comes in, and we see that it's at 6 meters, the intensity is going to be 1/4 as much. And of course, we went from 3 meters to 6 meters, so you're doubling the distance, and because it's an inverse square law, the inverse of doubled squared would be 1/4. So that answer makes sense. And then when we come over to part C, find the distance at which the intensity level is 40 decibels. Here's where we have to look at the equation that connects intensity to decibels. Decibels equals 10 times the logarithm of the ratio of the intensity of the sound to the threshold of hearing, if you remember that from screencast number 1. And so we basically plug our numbers in, and once again we're going to find that and then solve for R2, and we get our radius as 2.52 times 10 to the 4th meters. All right, the next topic we want to look at is something called the Doppler effect. This was discovered by Christian Doppler, and despite his first name, we have no idea. We have very little idea about what his faith was, what his worldview was, because he's one of those scientists who said very little one way or the other about what they believed or didn't believe. In all faiths, I imagine you have people who are outspoken and people who are very, very silent. But one important lesson here, of course, is if you are blessed with a changed heart because of the work of the Holy Spirit, you should be overwhelmed by that display of grace in your life, and so you would want to at least live, if not articulate, your faith in a demonstrative way. That's part of what we mean by sharing the gospel or being evangelical. So we don't know much about him in terms of his faith. Be that as it may, it's important to point out that Doppler did his work having to do with sound, but we now apply this also to light. And we talked about this a number of months ago when we talked about the red shift, the Doppler effect as it applies to light, which helped us to realize that our universe, not only is it expanding, but it is accelerating in its expansion. This is a revolutionary idea over the last century, which totally changed our understanding of our universe and totally confirmed that if the universe is expanding outward and indeed accelerating, that you just wind the clock backwards, which implies that at one point the universe was much, much smaller, and the farther back you go in time, you come to the point where the universe itself is just a point. And that obviously would support what Genesis 1:1 has said all along, and that is that this universe had a beginning because there was a moment in space-time where God created space-time and spoke the universe into existence. And in speaking the universe into existence, he spoke also the properties and the physics that govern the operation or describe the operation of that universe, of that space-time, and it has been expanding ever since. Now, as we look at the Doppler effect, we're going to come across a lot of terms and it can become very confusing. So you're going to see a lot of this little letter O here. And the little letter O is going to be the observer. Sometimes we use that little letter O to mean initial or the starting point. But in this case, this would be the velocity of the observer. And then over here, you're going to see V sub S. And a lot of times, especially in this context, we might say, oh, this is the velocity of sound, because there's lots of different kinds of velocities. We could have our initial velocity, we could have our final velocity, we could have, let's say, centripetal. But in this case, S does not stand for the velocity of sound, but stands for the velocity of the source. And that, in my mind, is one of the most common mistakes that physics students make when they're working with the Doppler effect, is to remember that V sub S, sub means under, V with the little s under it, refers to the source of the sound and not the speed of the sound. V without any subscript is the speed of sound itself. So that can be pretty confusing, and you want to be careful with that. So getting that out of the way, we have a number of possibilities here. The first possibility, when you have something producing a sound, is that the observer, whomever is picking up this sound, and let's say it's a person who is listening to the sound, is moving. The observer is moving, but the sound itself is stationary. So imagine over here in figure 14.9, you're on a bicycle, or you could be even a car with a window open so that you can hear sounds from outside the vehicle, and you're rapidly approaching the speed of sound. So you'll notice this arrow here is the vector representing the speed of the observer. And this V right here represents the speed of the sound coming from the source over here, which is stationary. Because the source is stationary, V sub S equals 0. Now, as the observer, as the listener of the sound is approaching the source of the sound, the amount of the distance through which the sound wave needs to travel gets shorter and shorter. If you think about pulses of sound being produced, in other words, think about these wave fronts coming from the source of sound. That sound is, as the observer is speeding towards the source of sound, the distance that the sound wave has to travel gets less and less and less. And as a result, the observer, the listener, is going to pick up an increased frequency. The frequency of that source, remember S stands for the source. The frequency of the source is going to appear to get greater and greater. So you have the actual frequency of the sound produced by the source, which is represented here. And then you have the apparent frequency of the sound picked up by the observer. The observed frequency, the frequency of sound that the person on the bicycle actually hears, actually goes up as he or she approaches the source of the sound. So when we come over to here, you can see that this equation means that the actual frequency of the sound, that's a constant, that doesn't change. Think of the sound producing object being a single tone that doesn't vary at all. Hopefully you heard that whistle. And because the observer is traveling towards the source of the sound, when we add the speed of the observer to the speed of the sound as it travels towards the observer, and compare that to the speed of sound in the denominator, you can see that the denominator remains the same, but my numerator gets bigger. When the numerator gets bigger, then the observed frequency is going to get bigger. And so the pitch of the sound is going to appear to get higher and higher as the observer, the listener, approaches the static source of the sound. Of course, the volume of the sound will get bigger as well, but we're not talking about volume. We're not talking about an increase in the volume. We're talking about an increase in the pitch or frequency. Now, the opposite is also true. If the person on the bicycle is traveling away from the source of sound, then my V sub the velocity of the observer is going to have a negative value. This is going to be a negative value, in which case now my equation becomes the frequency of the sound that is being produced. We're going to subtract the velocity of the observer because the observer is traveling away. And then, of course, we're going to compare that to the velocity of the original sound. And so the frequency that the observer hears is going to be smaller because when we do this subtraction in the numerator becomes smaller, meaning that my fraction inside the parentheses becomes smaller, which reduces the apparent the frequency of the sound that the observer hears. So when the observer is traveling away, and by observer we mean the listener, the frequency of the sound appears to go down. Certainly the volume goes down, but again, we're not talking about volume, we're talking about the pitch going down. All right, now let's look at case number 2. Case number 2 occurs in when we have the observer is going to be stationary, and this time the source of the sound is going to be traveling towards or away from the observer. This would be what you might experience if you're standing beside the road and let's say an ambulance or fire truck or police car is traveling towards you and then travels away from you. And what happens is, again, as the object producing the sound is traveling towards you and then later away from you, it's sort of starting to catch up to the sound that it produced a moment ago. That shortens the wavelength that it approaches you. It spreads the wavelength apart as it goes away from you. And so when we look at this equation right here, you can see that now the speed of the source, remember V sub s stands for the source. When the sound is traveling towards you, which means V sub s is positive, you can see that in the denominator, we have a V minus a positive number, which is going to make my denominator smaller. And when it makes my denominator smaller, it makes the value of this fraction bigger. And when the value of this fraction in the parentheses gets bigger, the frequency that the observer hears gets bigger. When you multiply that fraction by the frequency of the actual source of sound. And so again, you're going to hear the frequency get bigger and bigger. And I just did the sound with my whistle of the frequency getting higher and higher as it approaches you. And then at the moment that it passes you and begins to go away, we hear the opposite take place as the sound goes down. So when the object is receding from you, when the object is now traveling away from you, the speed of sound, of the source, is negative. And so when you subtract a negative in the denominator, now you get a positive sign. So now what happens is my denominator is bigger than the numerator inside the parentheses. And so the value of my fraction, V over V plus V sub s, gets smaller, and therefore the frequency down here, appears to tail off or get lower. The pitch goes down. Hopefully that made sense. Now you can picture this in the following way. Look at this diagram here on the right. What you have here is a light source that is above the page, and it's shining down on a trough, on a basin, a rectangular basin filled with water. Now, over the shadow of a solid arm over the water, maybe it's over the water by a centimeter or so, and at the end of it is an object that is bouncing up and down. So this thing is like a clapper on a bell that vibrates up and down, and every time it goes down, it creates a circular wave in the water. Every time it touches the water, then it comes back and goes back down and makes another one. So hopefully now you understand what this picture is like. And so the next thing we're going to be doing is we're going to be moving the vibrating object that is producing the concentric circles. We're going to be moving it to the right. So as this thing is moving towards the right, you can see that these waves get bunched up because the object producing the next wave is starting to catch up to the wave that it just produced a moment ago. As a result, on this side, the wavelengths get bigger because the object producing sound waves as they go this way have a greater distance to cover in order to get to the same place where the previous wave was made. And so you can see that my wavelength is bigger on the left, the wavelength is a little bit smaller on the right. Therefore, we have a higher frequency on the right, we have a smaller frequency on the left, representing the change in frequency as you go towards and the reduction in frequency as you go away. The frequency gets bigger as you move towards the right. It gets less as you go away towards the left. You're not physically moving, but as you look towards the left, away from the object producing these frequencies, it's producing a set frequency, the rheostat, if you will, on the device. It's causing this arm to go up and down and touch the water. That's constant. But as you move it towards the right, you can see that the frequency of the waves here is bigger, and the frequency of the waves over on the left is smaller. Now, we can put all of that stuff together. When we put all of that together, now we have a more complicated equation. This is the kind of equation you'd be given on a test. And you would have to know what the VO means, what the VS means, what the V means, the frequency of the source, the frequency that the observer hears. And again, by the word observer, we would mean the person or device that is listening to the sound. And you would have to know whether this speed here of the observer or speed of the source is positive or negative. You need to know that. Whether it's traveling towards or away, because that's going to really change the value. It's going to really mess up your answer if you don't get that right. And so basically you should analyze this fraction, the fraction inside the parentheses. You should analyze that fraction. Let me erase a lot of the mess here. That didn't work. You should analyze this fraction. Here's the fraction inside the parentheses. Here's the numerator, here's the denominator. And anytime your numerator gets bigger, you know that the pitch is going to go up, the pitch that the observer hears. And anytime the denominator gets bigger, you know that the pitch is going to go down. Now, there are two ways for the numerator to get bigger. One is by this being positive, and the other is by this one being negative. And there are two ways, of course, for the pitch to go down. The observed pitch that is heard go down, and that would be when this speed is a negative value, or when this speed in the denominator is a positive value. So you can analyze your answer and see if it matches what you would intuitively expect to get as far as the apparent change in the pitch of the sound that the observer is going to hear. So, a couple of important points. Choosing incorrect signs is one of the most common mistakes made in a Doppler effect problem. And so you should use this rule that toward is associated with an increase, and going away from is associated with a decrease. Common mistake number 2 is to accidentally get the numerator and the denominator reversed. We've got the observer in the numerator, we got the source, the speed of the source in the denominator. So this book suggests that you may want to rearrange your equation so it looks like this, and it allows you to keep the observers on the left side and the source terms on the right side. But also remember that sometimes your velocity is going to be positive, sometimes negative. Sometimes your velocity of the source is positive, sometimes it's negative, and you got to keep that straight. All right, let's come over to this problem right here. We have a train moving at a speed of 40 meters per second. It sounds its whistle. And this has a frequency of 500 hertz. And by the way, it just occurred to me, I wonder if as you listen to my screencast at a higher speed than the speed at which I'm speaking, I wonder if the pitch of my sound doesn't change. That would be interesting. Determine the frequency heard by the stationary observer as the train approaches the observer. And now you're given the ambient, you're given the room temperature right here. Ambient is the room temperature. Now this is pretty common in sound problems where you're given the temperature in Celsius and you're going to have to use that to calculate the speed of sound at that temperature. And that's the first thing that's done right here. We take our 331.5 meters per second, and you can either do the plus or minus 0.6 meters per second for every degree change in temperature, or you convert your temperature into Kelvin, which is what they do right here, and then take the square root of this temperature compared to the temperature at 0 to get your new speed. And notice that when the temperature is above 0, you're adding, which means your speed gets greater. If we had a temperature below 0, we would have a negative sign right here, and then your numerator would become smaller, and therefore your speed of sound would be less than 331 rather than greater than 331. And now we're going to plug our numbers in. My speed of the observer is 0 because the observer is stationary. The speed of sound is 40 meters per second, and it is positive because it's coming towards rather than going away from the observer. This negative sign is there by definition in the problem, so you're subtracting a positive value. You're subtracting a positive speed, and that gives you this pitch right here, 566 hertz. And so if we compare that to the original speed, which is 500 hertz, this makes sense. We expect a higher pitch because the source of sound is traveling towards the observer. So we would expect the Doppler effect to mean an increase in pitch. Now, of course, if you were traveling away at the same speed, you should get a smaller pitch. All right, let's look at another problem, the noisy siren. And so you have an ambulance producing this siren, traveling at 75 miles per hour. And right off the bat, you should say, okay, I'm going to have to do a conversion into the metric system here, into meters per second. And it's producing a pitch at 400 hertz, which means the operator of the ambulance is always hearing a pitch of 400 hertz. But a passenger in a car that's traveling in the opposite direction at a speed of 55 miles per hour, supposedly the speed limit, that's not what that passenger is going to hear. And so in this problem, you're given the speed of sound, or you could have been given the temperature, and then you could have calculated the speed of sound from the temperature. In any case, the speed of sound at this particular temperature is above 331, so we know the temperature is above freezing, and the speed of sound is 345 meters per second. And so obviously, like I mentioned earlier, you have to convert your miles per hour into meters per second. So we get those two different speeds, and now we can plug them into the equation. Now the speed of my observer, which is the person in the car, that goes in the numerator. And it's going to be a positive value because you're going towards the source of the sound, which is the ambulance. and of course the ambulance is also going towards you. And then we take the speed of the source, which is the ambulance, and we put it down there. Remember that negative sign is naturally in the denominator, and the speed of the ambulance is positive, so you're subtracting a positive number. Here's my speed of sound in air. Here's my actual frequency that is being produced by the siren in the ambulance. And we see that the pitch is going to be greater than 400. And we would expect a pitch higher than 400 for two reasons. Reason number one is because the ambulance is traveling towards you, and reason number two is because you are traveling towards the ambulance. And then we can come down here and compute the observed frequency as the ambulance and the car recede from each other. So now when you're going away, this becomes a negative sign, and this becomes a negative sign, and putting a negative sign in the numerator causes the numerator to become smaller, which implies you're going to get a smaller pitch or frequency of the observer. And putting that negative sign in the denominator means you're going to have minus a negative, which is going to be positive, create an addition, which makes the denominator bigger. And when the denominator gets bigger, that means that this fraction gets smaller also. And so for both reasons, you would expect a smaller pitch than your original 400 cycles per second, and it is smaller. Now, the last thing in this unit is to talk about shock waves. And shock waves address the question, well, what happens when the source speed catches up to and then gets greater than the velocity of the sound? What if you actually are traveling so fast, you're traveling faster than the speed of sound? Now, you might have heard of the term Mach, named after an individual. If you're traveling at the speed of sound, you're actually traveling at Mach 1. If you're traveling at twice the speed of sound, you're traveling at Mach 2. You may have heard that terminology before. But when you begin to catch up and exceed your speed of sound, we can diagram it like this, and then actually take a picture, which we'll comment on in a minute, and see that this is the case. So imagine that initially I have the observer of the sound, right here, and it's producing a sound wave, which at a certain amount of time is going to be this distance away. And then as this source moves towards the right, at some point it's going to be there, and more recently there, and even more recently there, and more recently there, and right now at the moment it's right there. So this is the one that's farthest behind, so the sound wave traveling out has had the greatest distance to travel. And then when my sound is, let's change the color, is right here, the sound wave has not had as great a time to travel outward. It's only that far away. And then right here, now my sound wave has only traveled that far away. And then right here, now my sound wave has only traveled that far away, and so forth. And the point being that if we connect all these tangents this way and connect all the tangents this way, we create what is called a bow wave, not a bow wave, like in a rainbow or a bow and arrow. This is called a bow wave. Think of OW being ow or ouch. Or the front of a boat is sometimes called the bow of the boat or the prow of the boat. The back of the boat, by the way, would be called the aft. So the back in terms of naval terms. And you also have terms like port and starboard. And the port side is the left. The word left and the word port both have 4 letters. And the starboard side is the right side. we're not going to be worrying about that in this particular discussion, just so you know these naval terms. But the aft part of the boat is the back of the boat. And so the bow of the boat, sometimes called the prow of the boat, is the front of the boat. So we're talking about a bow wave. And you can see that right here. You can see that right there, and it looks like what I drew in green over there. So this is the bow wave, sometimes called the shock wave. And when this is made out of compressed air molecules in sound, it can create what we call that sonic boom. Because remember, we're going at greater than the speed of sound, which modern jets do all the time, supersonic speeds. And it can create that sonic boom. In fact, a very fast jet will produce one sonic boom when the front of the wave catches up to and exceeds the sound that it produced a moment ago. Because remember, sounds are traveling towards the front of the jet, just like they're traveling behind the jet in all three dimensions, of course, and then the tail of the plane as well. And if the humidity is right, you can actually create, and there's a screencast, not a screencast, but a video on canvas that shows this bow wave produced by a jet, where the density of the air with the water vapor in it is such that you have this conically shaped mass of air, cloud shape, because of the water vapor in the air. And we have one more topic to cover, interference of sound waves. And if you look at this particular picture on the right, we have a speaker right here producing sound waves, and it enters a tube. And the tube splits into two pathways. One goes up and one goes down, and both tubes reunite over on the far side. And the difference is that the upper tube has a larger tube over it, sort of like a trombone slide. And this trombone slide can be made to move farther away or made to move closer, changing the path length of the sound that's going to be going clockwise around the top compared to the sound that's going counterclockwise around the bottom. Hopefully you followed that discussion. And the point being is that when the path of the sound, part of the sound that travels this way in the clockwise direction, when that pathway is exactly the same as the counterclockwise pathway, the two waves are going to reinforce each other. That means you're going to have compression on compression and rarefaction on rarefaction. Or we could say, if we're representing a wave with a transverse wave symbol, you have crest on crest and trough on trough. They reinforce each other. We can also use the term and say that they are in phase. They are in phase when crests are on crests and troughs are on troughs, reinforcing each other. We call that constructive interference, and you're going to hear your loudest sound. You're going to hear your loudest sound. And that's going to happen when this wave right here, the sound traveling clockwise, travels the same length or travels one wavelength longer or two wavelengths longer or three wavelengths longer, because any one of those conditions will result in the clockwise wave going across the top of our picture, arriving at when the bottom wave travels through the counterclockwise direction in such a fashion that crest is on crest, trough is on trough, compression on compression, rarefaction on rarefaction. Again, sound is a compressional wave, but sometimes we like to represent it as a transverse wave. So, but the point being that as long as you have some multiple n of whole wavelengths, you are going to get constructive interference. Now, what if the pathway of the sound going over the top of the picture, in other words, what if we take this trombone slide and move it inward or outward by half a wavelength, creating a path where the sound has a half wavelength shorter or a half wavelength longer to travel? Well, when that happens, you're going to get a compression from one wave matching a trough from the other wave. You got a wave going over the top and a wave going over the bottom. Another way of saying that is the wave going counterclockwise compared to the part of the wave going clockwise. You're going to get a crest on trough or a compression on rarefaction, and they are going to cancel each other out. So whenever your path difference is a fraction of a half of a wavelength, 1/2, 3/2, 5/2, 7/2, that additional half wavelength or multiple of the half wavelength, every other half wavelength, is going to create a destructive interference. It's going to cancel out the sound. And so at least as far as the sound that's coming through the tube, you won't hear anything. You might hear some ambient sound from around the room, but it cancels the sound out. And that is because they are 180 degrees out of phase. And that is going to produce cancellation. Now, if you're in a auditorium somewhere, there are oftentimes dead spots in the auditorium if it's not designed very well. And even when it's designed extraordinarily well, there's often a few chairs here and there where the sound bouncing off the walls and the ceiling and so forth arrive at your seat in such a way that you get some cancellation or some muffling of the sound. But ideally, in a good auditorium, just about every seat is in such a position so that you don't get a cancellation of the sound and you get your best sound reception. So, in this particular problem, we have two speakers that are 3 meters apart. So here's one speaker there, here's one speaker there. Here is the halfway distance between them. And you'll notice that we're going to take our listener starting off here, and it's going to move off to the side a little bit by 0.350 meters off to the side. You're given the speed of sound, and we want to find the first minimum. Now, the first minimum is the language for where's the first place where we're going to have cancellation or destructive interference. If it was asking for the first maximum, we would say, where's the position where we're going to hear the first reinforcement or constructive interference? But because it uses the word minimum, we're looking for destructive interference, and so therefore we're looking for, and I'm down here now, for this half wavelength additional distance. So what we're going to do is we need to find the distance of the path. We're going to have to find R1 and R2, and we can use the Pythagorean theorem to do that, and we get these two values. And then we can plug those two values into my equation, because the difference in those two values, R2 minus 1, is the additional path length that the sound is going to have to travel from one speaker compared to the other speaker, because the observer moved away from the midpoint. And we find that that additional change in wavelength is 0.26 or a quarter of a meter, just about. And we can plug that in now and find our frequency, because remember, velocity equals frequency times wavelength. This is the kind of equation you should memorize. And when we're talking about light, just talking about some chapters coming up in the future, the speed of light is frequency times wavelength. So it's a good equation to remember, and I'm just commenting on that incidentally. But velocity equals wavelength times frequency. And so therefore we're going to get this pitch, 1,300 hertz. and we're going to pick up with standing waves in the next screencast.